Hello, I'm Jim Handy, and I'm here to give you a presentation about compute and storage and how they're moving together. First of all, a little bit about who we are, Objective Analysis. We're a market research firm with a focus on memory and microcontrollers. Small firm with 3 analysts. We've been around for a number of years and are now participating in SNIA conferences and making presentations about some of the technologies that we know. We're based in Silicon Valley. And one of the things that we're very proud of is our forecast accuracy. This is something that I'm not going to walk you through, but you can look at it on the Objective Analysis website. It tells you that basically we understand the market well enough that we can tell where semiconductors are going, but also we understand the technologies that drive the semiconductors. And that's important to making sure that things fit in the way they should. So what am I going to talk about today? Well, we've got problems with compute and memory, compute and storage that can be solved to make computing a whole lot faster and better than it is today. And the ways that we're going to do that, I'm going to talk about, are moving persistence closer to compute. We'll be moving persistence into the CPU, moving compute into memory, and moving compute into storage. And I'll talk about each of those, the challenges with them, and why they're of benefit, and then I'll summarize at the end. So let's talk about the problem. This is a chart that I very often will use, both in SNIA presentations and in other presentations. It shows the memory storage hierarchy. You can see at the far left-hand side at the bottom is tape storage, and then it moves up to hard drive, SSD, 3D crosspoint, and then changes over to memory and DRAM, and then 3 levels of cache inside the processor. The chart's x-axis is the price per gigabyte, and that goes in orders of magnitude. So it gets more expensive as it goes off to the right. And the bandwidth is on the vertical axis. It gets faster as it goes up. So the fastest and the most expensive thing is the L1 cache inside the processor. I didn't put registers on this, but they are also an important part of the memory storage hierarchy, but they're handled a little bit of a different way. The way that different things fit into this memory storage hierarchy is that as long as they are cheaper than the next faster technology and faster than the next cheaper technology, then they will fit in. If they don't fit these criteria, they don't fit in, they don't make economic sense to include in the computer. What needs improvement in this hierarchy? Well, storage is persistent, but you notice that it's all down in the lower left corner. It's slow, but it is cheap. And memory is volatile. It loses its contents, but it's fast, but it's expensive too. So those are problems with that. And also the fact that storage is persistent and memory is not persistent also means that data has to be managed back and forth between the two. But the trouble is that when you're managing this data back and forth, and when the data is going into the processor, it goes through buses or it goes through storage interfaces. And those interfaces are bottlenecks that take an awful lot of power to perform tasks in. And the faster they go, the more power they consume. So data movement is a big power waste. And so it's very natural that people would like to move persistence closer to compute and maybe even move the memory closer to compute. Intel is doing that with their Optane memory. This is formerly known as 3D crosspoint memory, and it's a good fit for the memory storage hierarchy, as you saw in that diagram that I showed before, the blue circle towards the middle. It's faster than flash SSDs, but slower than DRAM. And it's cheaper than DRAM, but more expensive than SSDs. So it's, right in that hierarchy. But it does require significant system support. The operating system, applications programs, even the DDR bus that it goes on to when it's used in a DIMM, and the processor itself has to change for this. There have had to be certain flush instructions on the caches for Intel's architecture. And the processor has had to also put in special hooks in the memory management unit and also get support for a new bus in order to support the Optane memory. These are all very big jobs to do, even though it seems like a very natural thing to put this in. SNIA has taken a great amount of effort to put together the software side of this, and they've put together the NVM programming model. This is a way for applications to directly address the persistent nature of persistent memories, or to access it. Well, they can access it either as memory or as standard block storage device. And also the operating system can access it as a block storage device through normal calls. So you've got two options in your application program. Either you can rewrite the application program to go direct to the non-volatile storage, which is shown on the far right-hand side of this chart, or the application program can be unmodified and can go through a regular file system that has been made PM aware. But to make that aware, then the operating system also needs to be changed. And so this model has put together a way that right now Linux and Microsoft's Windows operating systems are able to support the Optane memory and other persistent memories and actually take advantage of their persistence. But that was a lot of work to get that put together. And new things like that do tend to take an awful lot of work. And yet there's still a lot that needs to be done. The bus speed for Optane memory is different for reads and for writes, and it's also different than it is for DRAM. So we have non-deterministic bus speeds, but the DDR bus doesn't like that. And so CXL has been presented as a possibility to change that bus around. And I wouldn't be surprised to see that being used in the future. Also, the memory management unit, which is hidden inside the processor, needs to be adapted so that it supports the non-uniform memory architecture, or NUMA, of this. Non-uniform meaning that you've got volatile and non-volatile memory on the same bus. And so now your MMU has to understand which part is volatile and which part is non-volatile, and be able to communicate back and forth with the application program about what goes where. And this is for varying sizes of these kinds of memories too, that you'll have one system that's got a large volatile memory and a small non-volatile memory. You'll have another system that has a large non-volatile memory and a small volatile memory, and your software needs to be able to perform without having to know the particulars of the system. The MMU helps with an awful lot of that. There's another issue that I haven't talked about, and that's a context switch versus polling. I'll talk about that with the next slide. And then how do you support off-the-shelf applications programs? These are considerations that had to go in there. And then finally, standardization across multiple platforms. I spoke about that a little bit when I was talking about the different sizes of volatile versus non-volatile memory. So these all have to be worked out. A lot of it has been with the non-volatile memory or the NVM programming model, but there are still issues that need to be done, for example, with AMD processors if they're to support Intel's Optane. The reason why I decided I'd have a separate slide for context switches is because this is a little bit of a strange concept. Context switches are performed every time you have an interrupt, and all I/O is driven by interrupt. This is when I say I/O, I mean disk interfaces, SSD interfaces, tape, anything like that does a context switch. A context switch is a slow operation in a processor, and it's never had to be fast before, because what it does is it stores everything that's in the registers and the current state of a program onto the stack before it allows, and it also puts in new values in the registers before it allows a subroutine to be invoked, which then starts handling the I/O. Now, that delay is very tiny compared to a hard drive access, or even to an SATA SSD, or even an NVMe SSD. But when you get to having persistent memory on the CXL or on the DDR bus, then all of a sudden that becomes an appreciable part of the program, and it ends up slowing the system down. So what we've got are today's Optane programs, ones that use the Optane DIMMs, are using polling. They're actually stopping the processor and having it go through an interrogation loop to be able to tell when the memory has done this thing that it's supposed to do. And that's something that needs to be addressed from a hardware standpoint. We'll see some changes and possibly, new ways of switching between threads in order to handle the Optane type interface. So let's move to persistence in the CPU. Why is persistence happening in the CPU? Well, it's because of a strange thing that's happening in semiconductors. And I'm not expecting for a lot of semiconductor experts to be in the audience, but basically you've probably all heard about Moore's law, which is the fact that the number of transistors has been doubling on a chip every 2 years or so. And that's been going on for a very long time. Well, certain technologies are starting not to be able to do that. The reason why NAND flash moved to 3D NAND was because it stopped scaling at 15 nanometers. That's the process geometry. That's the size of the transistor on the chip. NOR flash actually has stopped already at 28 nanometers. Now, this chart shows those nanometers, the NM figures down at the bottom, with the smallest processes on the right and the largest processes on the left. This is a backward series because of the fact that it kind of matches what's going on with time, that you've got yesterday off on the left-hand side of the chart and today on the right-hand side of the chart. Now, typically prices on the vertical axis have been going down in proportion to the process shrinks. But with NOR flash, then the technology stopped shrinking, and so the costs stopped going down. And that's something that's driven companies to put more expensive technologies, as represented by the black curve on this, to put them into research, so that over time, as NOR flash levels off, as the red line shows, that the black line will eventually come below NOR flash's cost, because even though it's a more expensive process, it's going to be able to shrink smaller and get smaller there. So it's a very attractive thing for use in on-chip memories for things like ASICs and microcontrollers. There are several candidates that are being discussed to do that, and there are a number of places you can go for information. We've got a report on it, and I think that there are a lot of places on the web that you can go to learn more about these if you want to. But that isn't really the subject of this conversation. I'll just say that a lot of candidates are trying hard to get into this marketplace. There's magnetic RAM, MRAM, resistive RAM, ReRAM, phase change memory, which is PCM, which is the basis for Intel's Optane, and ferroelectric RAM, or FRAM. So these are being worked on as alternatives to NOR flash to allow that scaling to continue. Static RAM, which is used as a scratchpad memory in microcontrollers, but it's also used as cache memories in larger processors, that is also challenged. It seems to be leveling off already. And so both of these technologies are up to be replaced. There are some microcontrollers that are already using some of these technologies. So you notice that largest block down at the bottom, STT-MRAM, that is an MRAM, a magnetic RAM, that is being used on a microcontroller. As microcontrollers first start to adopt this, they'll wring the issues out of the processes, and they'll get the production scale up high enough that it will become a cost-effective way of replacing other technologies, and it will become cheaper than SRAM. And there are benefits to having persistent caches, that they'll offer reduced energy consumption because you won't be needing to persist things out to memory. You won't have to go across the bus. They'll also give you faster transactions in online transaction processing, but also you'll get a better total cost of ownership in your data center by being able to reduce the amount of traffic that is going across on the bus. But the trouble is with persistent caches, all of that infrastructure that I was talking about with the Optane and the SNIAP non-volatile memory programming model and the MMU and the processor changes and all that, that all needs to change again. And it even goes down to the BIOS. The BIOS needs to understand that the processor has non-volatile elements that it didn't used to have. And it's also kind of an interesting problem, is that if you have a problem with your processor, you can't simply reboot. You have to reboot and tell it to ignore what's inside the persistent memory, because the persistent memory may be corrupt. You'll also need operating system support like you have with the SNIA programming model, but this time for cache. You'll need application program support that will understand that there might be things that are persisting inside of the cache memory. Standards will have to be written for that, and you'll need a lot of hardware support. So these are all important issues that will have to be fixed for persistent caches. But then after that, then we're going to move to persistent registers, and that's going to make things even more difficult. So this is a good thing, actually, for you. Something that I didn't mention before, and I meant to, is that everything that you're hearing so far is stuff that if you work on it, it's going to improve your resume if you're a software programmer or even a hardware engineer. So these are things that should really bolster your career if you were to focus on them. So they're all, good technologies. They're just challenging good technologies. So what becomes persistent in the system if we do that? It's kind of interesting to look at that. You've got the things that you would expect to be persistent: your tape, your hard drive, your SSD, and your 3D cross-point memory. Those all, everybody knows those are going to hold on to things. But if you start turning your caches into persistent memory, then all of a sudden you've got L1, L2, L3 caches that save data. Now, it might be that the L3 cache is the first one to get there because today's technology is not sufficiently fast to be able to replace the faster caches, the L1 and the L2. But eventually those will be there too. Now, what's strange about this diagram is right smack in the middle of it is DRAM. And DRAM doesn't look like it's going to be replaced by any non-volatile technologies anytime soon. However, it does look like it is going to stay there as a volatile memory. And so the systems are going to have to understand that not only are some parts volatile and some parts are non-volatile, but that it's broken up kind of unevenly in the system. And that's going to be a challenge. Some people have said that one of the ways of getting past some of these challenges and of speeding processing up is to move compute into the memory. And that makes perfectly good sense. They're all chips. And so you can take a memory chip, you can put compute into it. And there are companies who are actually trying to do that. There's the Venray is one of the companies that makes something they call the Tommy processor. There's another company called Natural Intelligence Semiconductor. It spun out of Micron Technology, who actually originally dabbled with this. And their processor is called Automata. And then finally, you've got a new startup that's called UpMem, which is really supposed to be UP for microprocessor and MEM for memory. Let's look at each of these. So the Tommy architecture, you can tell that it's drawn by a hardware guy. These are block diagrams of the registers and the caches and that sort of stuff. It's a very standard kind of a processor architecture, a kind of a weaker architecture, like ARM is, that doesn't promise all things. But it takes advantage of the fact that the internal buses inside a memory chip are just huge. These are tens of thousands of bits wide buses where you can perform all these operations at the same time. And if you don't have to take that data out of the memory chip and you can actually operate on it inside of the memory chip with a processor that may be a little bit slower than a normal processor, but still a processor, then you can get a lot of performance. The Automata processor is kind of a mind-bending thing because it is not a standard processor architecture. It's something that's optimized for a certain class of problems, which so far have been more appealing to academia than they are to other things. And we'll see something about that in a moment. And then finally, the UpMem is more like the Tommy processor from Venray, where it's a more standard processor. And what they've shown is instead of a block diagram, they just show a bunch of their DRAM chips on standard DRAM modules. And the way that you access these is the processor will write to the memory the same way that it always wrote to memory. And then it will write to a register that says, go execute that program that's stored alongside the data in the memory. And the thing just rips through the data at an incredible speed. Now, all of these are very fast for the problems that they solve. The the automata processor solves problems dealing with networks. That I use this diagram just to show how incredibly weird and sophisticated these things are. They're if grand challenge problems, and this network analysis one is one of those problems where they can actually figure something out considerably faster than a high-powered server, as long as it fits their kind of problem, which that's not really unusual. The GPUs that are currently being used for artificial intelligence training were developed just to do graphics, and then somebody discovered that graphics problems and AI problems were both massive matrix manipulation problems. And they said, okay, well, then we can use these for AI. This is the same kind of a thing where you've got a solution to a certain problem that might find its way into other problems. The UpMem, once again, we don't have something really technical on this, but they did give some benchmarks. The performance of the UpMem chip is the yellow part in these various bars. And I'm not going to leave this on for too long. You can download the slides if you want to look at it more carefully, or even just go to this company's website. But their processor, on the top line, you can see they say that it's 35 times faster in doing the Xeon server problem, for whatever this particular problem is that they've got there, the 5-word string search. And it offers 11 times more throughput. For genomics, they're showing that it's 10 times faster than a Xeon server. So, this is something that does really perform very well. But the technology is not really growing, and the reason why is because memory cost is scale-based, that you have to make a lot of chips to make them cost competitive. Low-volume parts cost a lot more to produce. And until that cost goes down, then the cost performance doesn't work. That even though you might get 11 times as much performance, if it costs more than 11 times as much, then it's a more expensive solution. Another problem that I've mentioned before is the support systems. They don't already have operating system hooks for this, compilers that understand it and can write code that takes advantage of it, and applications programs that also harness into it. So these are very big, difficult problems to work on. And then finally, user perceptions work against this, is that most people look at these chips and they say they're more expensive than memory, and memory is supposed to be cheap. So why exactly am I supposed to be using this? So these have actually gotten in the way of the adoption of these chips. And I'm not certain that they're going to be growing in the future, simply because these problems on the bottom two bullets are so very significant. It will be interesting to watch. And, as an industry analyst, I watch over these things. But I'm not sure that they're really going to go somewhere. And so, if you're looking for a place to build your resume, you might want to consider this, but maybe not. So moving compute into storage. That's when you actually bring the compute into an SSD or into a hard drive. People have tried it with hard drives. And there are several companies that are working on this right now. NGD, which used to stand for Next Generation Device, ScaleFlux, Idetacom, which is an interesting company, very strong participant in SNIA, who makes an NVMe appliance that plugs next to NVMe storage and just takes control of the storage without the processor really even knowing about it. NetInt is another one. I don't know an awful lot about them. Just last week, Xilinx and Samsung made a joint announcement that Xilinx is making a chipset with Samsung support for computational storage problems. So basically, anybody who wants to can get into this marketplace and make their own computational storage machine. And there was a company that worked for about 3 years on this problem, NVXL. Their website seems to have kind of gone away about a year ago. So I'm not too sure what's up with them, but they also were in the marketplace recently. But there are more. We'll talk about those in a minute, though. The big benefit in this was pointed out by something that Micron Technology showed at the Flash Memory Summit, a trade show here in Silicon Valley that happens every year, usually in August, except with COVID this year. Then it happened in November, just last week for me, on November 10th through 12th. This presentation was about doing primitives for databases inside a highly modified SSD. And Micron just took one of their industry standard SSDs, and they put in a couple of MySQL primitives, and then figured out how fast they could run MySQL with 1 up to 8 drives on this. And you can see on the blue line that the thing scaled, the performance scaled in proportion to the number of SSDs that were on there. And it didn't look like there was any limit as to how far this could go, that they could add 100 SSDs, custom SSDs to do this. But they were just doing it as a kind of a, let's see if this works thing. And so they only made 8 of them. They showed that they only used 1% of the CPU bandwidth that they required for the the system that did not use computational storage. And so that green line represents a CPU working 100% as hard as it can to do this same MySQL problem. And they showed that you got twice as much performance with 8 disks as you got with the server by itself. Yet the server was only operating at 1% of its full capacity. And you were using 39% less power because you weren't shuffling the data around. It seemed like a really good solution. I was surprised that Micron didn't take it any farther, but they left it to other companies to do. There are a lot of companies that have done stuff like this. I talked about Micron with the last slide. There's one called Kinetic. Schooner, Virident, and Violin were all companies that made systems that were based on the same concept. And I'll talk about those in a moment. And even WD Labs for Western Digital Corporation made something they called a microserver, which was a hard drive that had a little server built into it. These devices that were made by Schooner in, I think it was 2006, their device came with a number of SSDs and a basic server, and it would offload MySQL or Memcached into that particular box. And so all the data would be in the box, the server would be in the box, and the real server that was doing most of the work would then just download commands of, for example, of queries that needed to be performed on the database. And the database would never move out of that box. The query would be performed. The answer to the query would then be handed back to the main server. Another company that tried doing this was a company called Virident, which later became just an SSD company and then later was acquired by Western Digital. I think Schooner was actually acquired by SanDisk, but neither one of these companies succeeded in that. And then another company, Violin Memory, they put together one of their memory systems and put Microsoft Windows Server in it. None of these systems met with success in the marketplace, and it's most likely because of the fact that they had all of these other parts of the solution that they needed to put together that they just didn't have. So the key considerations here is that there are not big barriers to entry in this marketplace. You don't need to design a new chip, which is tens of millions of dollars process. You just need to put together a system that's got SSDs in it, maybe inside of an SSD. Still, the R&D costs are pretty significant to do this, but the production volume is far less important than it is for a memory chip. You don't have this problem with the economies of scale that I was talking about with the memory chips that have processors in them. They all require support throughout the system, and that takes an awful lot of time to develop, especially in the applications, programs, and operating system. And they still have the problem that memory had, that storage should be cheap. And so these bottom 2 bullets are the same for processing and memory and for this. I think that those are the things that are most likely to get in the way of the adoption of this. But I'm bullish on this. I think that even though Schooner, Virident, and Violin didn't have success with this, there is acceptance in the hyperscale data center area for these. And so they're probably going to do well for themselves. So let me move to the summary. We've got data movement causing delays and also consuming a lot of power, and you'd rather have the data and the persistence close to the processor. So those are important key points. Persistent memory does help with that, and it's already here. Persistent caches and registers are going to be coming, and so they'll be an exciting new place to work. I'm not sure that in-memory compute is really going to go anywhere because of the cost issues that are there. And computational storage could end up being accepted. It will take some work for that to happen. But no matter what happens in any of these, it's going to require an awful lot of support. And that includes standards, that includes support from the top to the bottom of the software, and it will probably require an awful lot of support from the hardware to do that. Just a quick mention, there is a report on these emerging memory technologies. And so if you have any desire to learn more about that, then there is a report that you can look at for that. It's now available from Objective Analysis. And with that, I want to thank you and wish you good health in this very strange time.